name is Agata Goździk. I'm from the Institute of Geophysics, Polish Academy of Sciences. And today I will say a few words or even more about Northern Lights, a magic spectacle in the polar sky. This is really a wonderful spectacle, and I was happy to see that in the northern Norway, in one of the scientific stations in Norway. I was also visiting our Polish polar station, Hornsund on Spitsbergen, many times, but in during mainly summertime, so it was not possible to see Northern Lights there. But we have some videos taken by the members of our polar team wintering in the station, so I will share it with you. The basic material, the content of the material of today's lesson was created within the EduArctic 2 project, which was funded from EEA grants. Therefore, it's a combination of Interact and EEA grants. So we will start with this short video taken at our Polish polar station. On the map you see where Svalbard is located, and our station is in the southern part, located in the national park. And during watching the videos, please observe the colors and what type of movements, how the Northern Lights are moving around. And we will see two videos, one from the perspective of the polar station, so from the ground, and the other one from the space taken by NASA. So let's start first with the normal vision from the grounds. That was the perspective from the ground, and now we will watch it from space, thanks to NASA, a beautiful video taken. I hope you enjoyed the shows, and now a little bit more of science behind this spectacle. So we are calling Northern Lights also aurora. Northern Lights are visible in the North Hemisphere in the auroral oval, so basically latitudes 60-70 degrees. Northern Light in north, but we also have Southern Lights, which are called Aurora Australis, and are visible in the Southern Hemisphere, also in similar latitudes. So this auroral oval is around 60-70%, the most common, because we may also observe auroras in other latitudes, but this is the most spectacular and the most often visible part for auroras. And auroras also occur on other planets, so the planet Earth is not that unique in these auroras. So all the giant planets, Jupiter, Saturn, Uranus and Neptune, they have a strong magnetic field, and also phenomena very similar to Earth auroras are visible there. On other planets like Mars and Venus, we have similar lights. They are formed slightly differently, but they are caused by magnetic field, so combination of magnetic field and the gases in the atmosphere of these two planets. And the only planet that does not have any kind of aurora is Mercury, because it's too small to have its own atmosphere. It's very close to the sun, or very close, relatively close to the sun, and small so that the gravitation is not strong enough to take the gases and form atmosphere around it. And now I will show you absolutely great animation from TED talk, animation prepared by Michael Molina about aurora, how it's formed and how it starts, and the whole way from the sun to the earth. And you will learn more about the physics behind that.
Every second, 1 million tons of matter is blasted from the sun at a velocity of 1 million miles per hour, and it's on a collision course with Earth. But don't worry, this isn't the opening of a new Michael Bay movie. This is the journey of the polar lights.
The northern and southern lights, also known as the aurora borealis and aurora australis respectively, occur when high-energy particles from the sun collide with neutral atoms in our atmosphere. The energy emitted from this crash produces a spectacle of light that mankind has marveled at for centuries. But the particle's journey isn't just as simple as leaving the sun and arriving at Earth. Like any cross-country road trip, there's a big detour and nobody asks for directions. Let's track this intergalactic voyage by focusing on 3 main points of their journey: leaving the sun, making a pit stop in the Earth's magnetic fields, and arriving at the atmosphere above our heads. The protons and electrons creating the northern lights depart from the sun's corona. The corona is the outermost layer of the sun's atmosphere and is one of the hottest regions. Its intense heat causes the sun's hydrogen and helium atoms to vibrate and shake off protons and electrons, as if they were stripping off layers on a hot, sunny day. Impatient, and finally behind the wheel, these free protons and electrons move too fast to be contained by the sun's gravity and group together as plasma, an electrically charged gas. They travel away from the sun as a constant gale of plasma, known as the solar wind. However, the Earth prevents the solar wind from traveling straight into the planet by setting up a detour, the magnetosphere. The magnetosphere is formed by the Earth's magnetic currents and shields our planet from the solar winds by sending out the particles around the Earth. Their opportunity to continue the journey down to the atmosphere comes when the magnetosphere is overwhelmed by a new wave of travelers. This event is coronal mass ejection, and it occurs when the sun shoots out a massive ball of plasma into the solar wind. When one of these coronal mass ejections collides with Earth, it overpowers the magnetosphere and creates a magnetic storm. The heavy storm stresses the magnetosphere until it suddenly snaps back, like an overstretched elastic band, flinging some of the detoured particles towards Earth. The retracting band of the magnetic field guides them down to the aurora ovals, which are the locations of the northern and southern lights. After traveling 93 million miles across the galaxy, the sun's particles finally produce their dazzling light show with the help of some friends. 20 to 200 miles above the surface, the electrons and protons meet up with oxygen and nitrogen atoms, and they sure are happy to see each other. The sun's particles high-five the atoms, giving their energy to the Earth's neutral oxygen and nitrogen atoms. When the atoms in the atmosphere are contacted by the particles, they get excited and emit photons. Photons are small bursts of energy in the form of light. The colors that appear in the sky depend on the wavelength of the atom's photon. Excited oxygen atoms are responsible for the green and red colors, whereas excited nitrogen atoms produce blue and deep red hues. The collection of these interactions is what creates the northern and southern lights. The polar lights are best seen on clear nights in regions close to the magnetic north and south poles. Nighttime is ideal because the aurora is much dimmer than sunlight and cannot be seen in daytime. Remember to look up at the sky and read up on the sun's energy patterns, specifically sunspots and solar flares, as these will be good guides for predicting the auroras.
I hope you liked this animation, and now it's your turn. If you have the worksheet printed, you may write directly in the worksheets. If not, you may use your notebooks. And I will be also waiting for your answers on chat. I would be happy to see your answers. So 3 simple questions. What colors may aurora have? It was explained in the animation, but also from the videos you see previously. And how would you describe the movement of aurora on the sky? So basically, if you meet someone that hasn't seen aurora and hasn't seen any video, anything like that with aurora, how would you describe this movement? And which atoms are getting excited and they are glowing to make this spectacle happen. So this is the task number 1 in your worksheet, and also please provide the answers on chat so that I know that you are ready with your answers. Okay, so thank you for the answers, and now we will go step by step how it all starts. So we know that the sun is bursting millions of tons of matter with enormous velocity. It's around 2.5 million kilometers per hour or even more. So it usually takes around two days to get from sun to the earth. However, if the burst is really giant and with high velocity, then it can be even shortened to around 10-12 hours only. And on this graphic, you may also see the relative size of Earth comparing to the Sun size. So you see that also the flare. So this the part. This is a solar flare, and this is really enormous, giant, relating to the size of Earth. And there are various types of solar activity, because the solar activity is the starting point for aurora. So solar flares. We also have coronal mass ejections, which give the most spectacular aurora. And the solar wind is a charge, the stream of charged particles released from the upper atmosphere of the sun, which are constantly moving towards the Earth, but also other planets, depending on which part of the sun is releasing this wind. And also now we will watch short video with coronal mass ejection. This ring here is covering the sun, and the rest are the coronal mass ejection. So see how big they are. This is a time lapse, and this is repeated 3 times. And you see that it lasts several hours, around 6-7 hours in total. So it's not like second, but we need to remember that these bursts are more or less the same size as the size of the sun. So it's really big. Okay. And now a few words about the solar activity, because the sun is active in some cycles, and scientists discovered, in fact, it was a hobby astronomer, so not a scientist, that first observed that there is some regularity in solar activity. And then scientists checked back what was written in observations, and at the moment we are in the 25th solar cycle. And you see here on this graph that scientists are observing a weakening trend in solar cycles for more than 40 years now. But if you observe it properly, you may also calculate how long does a solar cycle last. And this is a task number 2 in your worksheet. So have a look on the years on the x-axis, and you also see that on this graph you see daily sunspot number. So in the time of solar sun maximum, we have observed several sunspot every day, because it's per day. So this activity is really enormous. In the period of minimum activity, it's a few or even 0 sunspots per day. So I will also give you the correct number. It's 11 years, and as I said, at the moment we are in the 25th cycle. And for sometimes scientists at the beginning of this cycle, scientists were wondering maybe this weakening trend is so strong that we will not observe maximum in this solar cycle. And it was the Polish astronomer Dr. Mrozek that was first to spot the higher activity. So the sign that the next cycle really started. Okay, and again a video, because I think it's a nice explanation of the Carrington event. This is the most spectacular event that was registered by scientists, because we are not sure, maybe in the previous times before human appeared, or before we had some registration and observations of such events, maybe we had a stronger one, but from the time that we have observations and have some historical documents about aurora, we know that this event was the strongest one. And here what happened. So we heard that this kind of very strong phenomena may cause even some deaths, because these operators of telegraphs that at the moment, it was 19th century, they were working with telegraphs, got shocked, and some paper on telegraphs was on fire, etc. So it was really an enormous event. And there are some records, historical records, that even in China or in New York, so the places that are located much southern from auroral oval, so the place where we are usually observing auroras. The aurora was also visible, and it lasted very long because the light was good enough to read newspapers even during the night, only in the lights of aurora. So this was really something spectacular. And also, as you may read during the last part of the video, if it happened at the moment, we are so connected to all internet, Wi-Fi, GPS technology, that if it affects our magnetosphere so strongly, it would cause serious problems also for us, for the whole navigation and also internet connection. So you may imagine that it would be really difficult to survive from our perspective of nowadays. But of course, we have some protection because you know that the aurora current is very strong. Comparing to our current in the circuits at home, it's uncomparatively big, but we are protected, luckily. So what protects us is our magnetosphere. So this is something that tries to stop these solar winds and the charged particles, and it sends it first to the vicinity of poles, and also then it forms a kind of tail. So then it's pushed back from the Earth. But in the moment of a geomagnetic storm, so in case of very strong solar flares, the magnetosphere may become overwhelmed. So it's too much discharged particles that are pressing on our magnetosphere. And this is the reason that some particles from the tail, from this part, are coming back again. And they are coming parallelly to the lines of the magnetosphere, so they are coming where the close to the magnetic poles, and therefore we see the aurora in the vicinity of magnetic poles. Yeah, so here are also some observations. You see that we are not observing directly on the poles, but in this auroral oval I mentioned, and the same is on the southern hemisphere. So around 60-70 degrees we observe the best spectacles. Therefore, for instance, Iceland is so much appreciated by tourists who are trying to catch great photos or videos of aurora, because it's not that far, not that close to the pole. Okay, and some summary about colors of aurora, because the colors strongly depend on two variables. First, what kind of atoms are excited, and the second, the height above the ground where the particles are meeting atoms from our atmosphere. So excited oxygen gives mainly green. This is the most popular color of aurora, and this appears between 100 and 200, 300 kilometers. If the oxygen in the higher part, above 300 kilometers, gets excited, then it gives red colors, but it's very rare. Whereas excited nitrogen gives purple when it's around 100, 120 kilometers, and blue when it's close to the Earth, so below 100 kilometers. Okay, and now we have a short test. This is task number 7 in your worksheet. And so we have 4 options. Auroras may appear near the North Magnetic Pole, near the South Magnetic Pole, on Mercury, on Jupiter. Okay, so I hope you are ready now. So only Mercury doesn't have this phenomenon. And of course, we have more popular from human perspective, northern lights, because more people live here in the Arctic and close to this North Auroral Oval. But southern lights are as well appearing in the southern hemisphere. And now, true or false? The aurora occurs when highly charged particles from the solar wind interact with gases in the Earth's atmosphere. Is it true or false? And this is true. So this is basically how auroras are formed. And the most popular color of aurora is green. It's connected with excited atoms of nitrogen, oxygen, or argon. It's oxygen. And the last question. Auroras are mainly formed at altitudes 1 to 2 kilometers, 20 to 40, 100 to 200, or 500 to 1000 kilometers. Which is correct? Yes, that's true. 100 to 200 kilometers. That is the most often the part that is excited most often. Okay, and now it is your turn to, based on what you heard, prepare a mind map. You may use the worksheet task number 3, or you may do the mind map in your notebooks, or do it together with your teacher on the board. So whatever you like. And doing the mind map, think about some aspects like where it appears, what are the colors. You may also write what are the connections of colors to the atoms and attitudes. What are the excited atoms, at what attitude they are appearing, and what are the source of energy, so how it all starts. And I have a short wrap-up at the end, so you may have a look at that. Maybe it will help you also with the auroras, with the mind map.
Have you seen this amazing video of the Northern Lights? The footage was filmed in Sweden over Christmas 2013, which got us thinking about the aurora borealis. Here are 5 remarkable facts you should know. I'm Sophie, and welcome to the countdown. What causes an aurora? Well, the Earth is surrounded by a magnetic field, which normally helps deflect harmful radiation. When charged particles from the sun, known as the solar wind, fly towards our planet, the field speeds up those particles and directs them towards the magnetic north and south poles. As the solar wind hits our atmosphere, the charged particles collide with atmospheric atoms and molecules and transfer their energy. These gas molecules then spit that energy back out in the form of light. Our atmosphere is mostly made up of oxygen and nitrogen, which produce a variety of colors. Atoms of nitrogen release blue light, while 2 nitrogen atoms bonded together give off a purple hue. The color also depends on altitude. Oxygen releases green light above 100 kilometers, but switches to a reddish color above 240 kilometers. And when colors combine, they can produce other shades, like pink and yellow. The aurora can be a single hue or a shimmering rainbow. Unfortunately, the solar activity that gives us auroras also has some unwanted effects. On the planet's surface, charged solar particles can interfere with satellite communication, along with radio, television, and telephone signals. Navigation instruments, like compasses, become unreliable. The solar weather can even cause electrical surges that interrupt the power grid and sometimes result in power outages. Auroras have fascinated humans for thousands of years. This cave painting, which dates back to 30,000 BC, may represent the earliest observation of the phenomenon. But it wasn't recorded in more detail until 2600 BC, when a Chinese manuscript described it as strong lightning. Most early attempts to explain the aurora fell flat. A drawing from 1570 AD attempted to illustrate it as a line of candles hovering above the clouds. In 1619, Galileo thought reflected sunlight was causing the light show, so he named it after the Roman goddess of the morning. It wasn't until the 20th century that Norwegian scientist Christian Birkeland suggested molecules in the atmosphere were responsible for the light show. The aurora borealis and its southern cousin, aurora australis, are generally located over ring-shaped regions roughly 4,000 kilometers wide, which circle the north and south poles. But when an aurora is putting on a big show, the ring spreads over a much larger area. On rare occasions, aurora borealis can be seen as far south as Texas. If you want to see an aurora yourself, you can either travel north or south, or just wait for a particularly large aurora. You'll want a clear dark night, and you should avoid heavily populated areas with a lot of light pollution. Then, just look up and marvel. I'm Sophie Bushwick, and that's your countdown. If you like our show, visit the Space Lab channel.
Okay, so now I hope after this wrap up, it will be relatively easy to create your mind map. And that's all from my side. Thank you very much.